Now let's have a look at what should we do if we do have multicollinearity in the sample that we have with us. So we are going to look into the remedial measures possible. So the thing that you should know is there are two very different schools of thought when it comes to remedial measures. The first school of thought says do nothing. Now the reason is that even though the influence of individual x variables cannot be disentangled, as we have seen, it is possible to find and accurately estimate a linear combination of these x variables with relative efficiency. By relative efficiency, I mean that the linear combination that has been estimated using the OLS procedure is still blue. So for practical purposes, sometimes this might just be enough. And if that is the case, then we follow the first school of thought, which says do nothing, do not bother about the multicollinearity. However, the other school of thought says that sometimes multicollinearity can be a severe problem. So they give a few rule of thumb procedures. Again, they are called rule of thumb because they are not hard and fast and they are not completely foolproof. As the empirical researcher, you will have to decide which of these methods of removing or reducing the problem of multicollinearity is suitable for the problem at hand. All right. So first rule of thumb procedure, like I said, is if you have a priori information. Now the source of this information, a priori means prior to the particular case at hand. So it is possible that previous empirical work or maybe theoretical deductions have given us the information which helps us have an idea about the nature and the extent of the relationship between the x variables. Now, if you have such information, you can explicitly build it into the model, and then using that relationship between the x variables, you can identify or calculate the individual coefficients. There's an example given here. Suppose a priori we believe that beta 3 is 0.1 times beta 2. Then you can actually build it into this model where instead of beta 3, you have replaced it with 0.10 beta 2. So the model that the net effect is that the model is yi is equal to beta 1 plus beta 2 xi plus ui, where your variable xi is a linear combination of x2i and x3i given in this manner, that xi is equal to x2i plus 0.1 times x3i. So if you have a priori information that the relationship between the two coefficients is of this sort, you can build it into the model. A more what happens in that case is you have gotten rid of, or you have explicitly addressed the collinearity, and here you are actually estimating only two coefficients, and based on this new coefficient you can always calculate beta 3, thereby finding out the individual influence of variable x3i on the dependent variable yi. Another procedure, this was suggested by Tobin, was to combine cross-sectional and time series data. He suggested this method when you are dealing with time series data and the variables at hand are very collinear. So if this one of these variables can be estimated using cross-sectional data, then its value can be plugged in to the original model and the modified model can then be estimated. Understand it, but you will understand it better if you look at this example. We have a time series data where you're talking about your dependent variable is the number of cars being sold. Now you're saying that the number of cars being sold is determined by the average price of the cars and the income levels of the buyers. T stands for time, so this is time series data. Our objective here is to estimate the price elasticity as well as the income elasticity of cars. Now, we know that over time, higher prices will be positively related or correlated to higher incomes, because only people with higher incomes would tend to purchase higher priced cars. So expecting this positive collinearity, what can be done is cross-sectional data can be used to estimate the income elasticity beta 3. So if cross-sectional data is available, you can estimate income elasticity from that and estimate a new regression model of this sort, where yt star is equal to beta 1 plus beta 2 log of price pt plus ut. Here the y star is nothing but the original y variable minus beta 3 hat. Remember, beta 3 hat is income elasticity which can be calculated from which has been calculated from the available cross-sectional data. Now the reason Tobin said this was okay to do that is because income elasticity is something that is relatively constant in a period of at a constant point of time. So he said so in this particular model which was used, different types of car prices which were being sold at a point of time were available, and the income levels of the buyers was also available. So they ran a regression on the cross-sectional data of the particular year and estimated the income elasticity, and then modified the model to get yt star and estimated this modified model. So remember, we are assuming that this cross-sectionally determined variable, in our example it was the income elasticity, is the same as the one that we would arrive if it had been a pure time series. So if this assumption is in any way, if it is wrong or misleading, it will obviously affect the quality and the reliability of our interpretation as well, right? Another method suggested is to drop a variable. So this is one of the simplest methods actually. If there is a case of severe multicollinearity between two x variables and you know that it is there, why don't you just simply drop one of those collinear variables from the regression? But if we do that, we run the risk of something called committing a specification bias or error. To understand this better, again, look at the example we have been discussing throughout. Consumption expenditure determination model, and there the x variables are two important x variables are wealth and income. Now we know from observation that wealth and income are highly correlated and collinear. So one of what this method suggests is drop the wealth variable, estimate the model using only the x variable income. But now what happens is, since wealth and income are both correlated, the coefficient that will be estimated in the model without wealth, that coefficient is capturing the combined influence of income as well as the wealth variable. Okay, to the extent that they are correlated, the more correlated income and wealth are, the more influence of wealth also will tend to get captured in that single coefficient. So what happens is, because we have dropped an important explanatory variable, the estimates that we have will be biased estimates of the true population parameter. So this is what is said called as committing a specification bias. This may again result in misleading interpretation regarding the true population parameter. So although it seems the simplest, it is one of the least favored remedies. Another method or method to deal with multicollinearity is to transform the given variables into some different form. For time series data, one of the commonly used transformation methods is to convert it into the first difference form. And the first difference form actually gets rid of some of the multicollinearity. I can give you an example, rather let me just show you what first difference form means. So say I have a 3 variable model and it's time series model. Remember, this is mostly used for time series. So you have yt being determined by beta 1 plus beta 2 x2t. The subscript t shows that it's a time series. T stands for time or the year, plus beta 3 x3t plus ut. Now we know that x2t and x3t for the same year are positively or collinear, positive or negative, I don't know. So if it is true for collinearity holds in the period t, the collinearity will also hold for the time period t minus 1, that is the prior period. So it will be beta 1 plus beta 2 times x2 t minus 1 plus beta 3 x3 t minus 1 plus u t minus 1. So whether the period is t or just before, the period just before, that is t minus 1, we know that the variables x2 and x3 are correlated. However, if I subtract these two, that is, I take the difference, this is why it's called the first difference. I take the difference as yt minus yt minus 1. Then beta 1 and beta 1 cancels, so I'm left with beta 2 times x2t minus x2t minus 1 plus beta 3 x3t minus x3t minus 1, and ut minus 1, I'm going to call it vt, right? So this equation in this form is called the first difference form. We are saying that while x2 and x3 are collinear in any particular time period, the difference between x2 and x2 t and x2 t minus 1 need not be collinear with the first difference of x3 variables. So you're taking differences of successive values of the variables. So this is one of the transformations that they talk about, commonly used in time series. Another transformation that they talk about is the ratio transformation. For example, if you are regressing you're using the regression model to determine the consumption expenditure, and your explanatory variables are population and GDP. Now we know that both GDP as well as population are highly multicollinear. So you can convert this using the ratio transformation. So in the ratio transformation, you can actually convert your dependent variable into consumption expenditure per capita, and your x variable will become GDP per capita, right? So in this way also, you have gotten rid of having two multicollinear variables, but without ignoring the important x variable population, right? But things to be kept in mind is that even these transformation of variables can lead to different problems. So you have gotten rid of multicollinearity, but you might have some other assumption which is not being satisfied. In particular, in the first difference form, you can show that the assumption of no autocorrelation, that is that your error terms are uncorrelated, that assumption need not be satisfied when you take the first difference form. Similarly, when you do the ratio transformation, it is possible that our error term, the assumption of homoscedastic error term, is no longer holding. So when you have situations of this sort, you have to be careful as to which method you choose. It is possible that to get rid of multicollinearity, you are getting yourself into much more trouble, because remember, even if you have multicollinearity, your estimates are still blue. But if the problem of autocorrelation or heteroscedasticity comes into your sample, your OLS estimators are no longer blue. As you shall see in the following lectures, both autocorrelation between the error terms and heteroscedasticity of the disturbance term, both of these result in the OLS estimators not being blue. Okay, so choose wisely. The next method is to find additional or new data. Remember, we said that while the variance inflationary factor is related to your collinearity between the x variables, it can be the variance inflationary power of this collinearity can be reduced if the variation of the x variables, that is the additional data or the sample size, can be increased. So if summation xj square actually rises, you can counteract the variance increasing tendency of VIF. But again, if you're working with data that has been collected beforehand or secondary data, it might not be easy or even practical. Sometimes the data collection is so costly that finding new additional data is not possible. And the sixth method is when you have polynomial regressions. By polynomial regressions, I mean something like yi is equal to beta 1 plus beta 2 xi plus beta 3 xi square plus beta 4 xi cube, and so on. So you have powers of the same explanatory variable being a part of the equation. So if you have a polynomial regression of that sort, expressing these explanatory variables in the deviation form can get rid or at least reduce the degree of multicollinearity. A few other methods which are not mentioned in detail are something called factor analysis, principal components analysis, and running of ridge regressions. Okay, so these can also be used to solve the multicollinearity problem. We are not going to go into the details of it. Okay, just remember these names. Finally, we come to the conclusion, which is that multicollinearity is not too much of a problem as long as the main objective of the regression analysis is prediction of what will be the dependent variable if the x variables values are given so and so. However, when one of the main objectives is the estimation of the true population parameters and hypothesis testing based on these coefficients, multicollinearity can prove to be a bit irritating. Okay, so like I said, even if you have multicollinearity in your sample, the estimators that you calculate based on the OLS method or the ordinary least squares criterion, these will still be blue. They'll be linear, they'll be unbiased, and in the entire class of linear unbiased estimators, these will have the minimum variance. But since the variance is quite large, the variance, covariances, and standard error terms, since they are quite large, using them for hypothesis testing and estimating the true population parameters, our accuracy will be limited. Well, that's it. That we'll wind up multicollinearity for the time being. Our next topic will be autocorrelation.